Hello and welcome to the product demo of SigmaXL version 10. The presenter for this video is SigmaXL co-founder and Chief Technology Officer John Noguera.
Today we're going to introduce SigmaXL version 10. We're going to give a brief background history of our company, SigmaXL. We'll have a quick overview of the menus and the resources that are available. We'll look at graphical tools, including the selection guide, heat map, histograms and descriptive statistics, Boxplots, Scatterplot Matrix, XYZ contour surface plots, and the analysis of means. And then we'll look at statistical tools, descriptive statistics, hypothesis test selection guide, two proportions test and confidence interval, two sample t-test, two sample comparison tests, one ANOVA, correlation matrix, and advanced multiple regression. Then we'll look at process capability and control charts. Our background history, so we've been around a while, since 1998, and the genesis of SigmaXL was working with Motorola University. They, in their external Six Sigma Greenbelt program, wanted an Excel-based product, and SigmaXL was the tool that we developed as part of, I was a contractor developing the materials, the training materials for them. That was it. That's how it started. It started with, in the context of a Six Sigma curriculum, and has grown ever since. So let me talk about the menus. And for the menus, I'm going to just show you the SigmaXL menu. I have a PowerPoint presentation, by the way. That PowerPoint will be available to you if you are interested. But when you click on, when you install SigmaXL, when you run it, you get a SigmaXL menu item added to the Excel menu. And under the SigmaXL menu, you have data manipulation. So things like subsetting, transpose data, stack subgroups across rows, generate random data, standardized data, and so forth. So your basic data manipulation. Your templates and calculators, including DMAIC and DFSS templates, FMEA, SciPoc diagram, charter, your control plan, and so forth. QFD. We have lean tools, basic lean tools. Then we have basic graphical templates, basic statistical templates. Some of these I'll show you during the demo. Probability distribution calculators, basic MSA templates, basic process capability templates, basic DOE templates, Taguchi DOE, and control chart templates. All right, so I just wanted to mention that the focus is going to be on the menu-based items. So graphical tools, we'll be spending more time here. And then statistical tools. And then briefly, we'll talk about the measurement systems analysis, process capability, design of experiments, control charts, and then reliability, Weibull, and time series forecasting. Again, these are tools that we won't cover here. Under resources, you have the SigmaXL help. And if you click on help SigmaXL guide, that brings up a PDF workbook. And this is a 1,000-page workbook. So you have lots of detailed information, step-by-step guide, and each of the tools are covered, including appendices with statistical details. Then we have other resources include online virtual menu. So under the online virtual menu, you can actually click. So for example, if I go here, graphical tools, heat map, this brings you to the heat map and you get a video, plus you get a scripted step-by-step instruction. You get the idea. That's for any item of interest. You can go to the virtual menu and it introduces you to the workbook contents, and typically that includes a video. Finally, in terms of resources, we also have YouTube videos. So lots of YouTube videos. We have 127 videos. So that's a good, helpful resource. So let me start with under graphical tools, the graphical tool selection guide. So one of the challenges when you have lots and lots of tools is what is the correct tool to use? And we created these wizards or selection guides to make that task easier. So first you start with what type of data do you have? Do you have continuous data or do you have discrete data? If you have continuous data, what is the purpose of the graph? Are you interested in a distribution? And if you're interested in a distribution, your options are basic histogram, histogram and descriptive statistics, histograms and process capability, histogram template, and dot plot. If you're interested in center spread and outliers, your options are box plots and multiple X box plots. Interested in confidence intervals, then you have interval plots, multiple X interval plots. Interested in time varying, well, then you can do a run chart or an overlay run chart. Are you interested in XY relationships? Then you have Scatterplots and Scatterplot Matrix. If it's XYZ, then you have the XYZ contour surface. Interested in sources of variation, you have multivary. Normality, you have the normal probability plots and the empirical CDF plots. And then you have the analysis of means. If you switch over to attribute, what is the purpose of the graph? To prioritize, then you have basic Pareto, advanced Pareto. Are you comparing? That's easy pivot and heat map. I will be showing you the heat map. Time varying, again, back to run chart, just this time is with discrete data. And then the analysis of means, some of the analysis of means charts are suitable for discrete data. So this one dialog helps you, especially for training purposes. Very nice way, kind of a gentle introduction to the tool. So this hooks into every graphical tool that is in SigmaXL. And by the way, we have a similar tool for hypothesis testing and a similar tool for control charts, and I will show those. So supposing that, let's say I have attribute data and I want to compare and I want to do a heat map because that's one of the graphical tools I wanted to show you. And then you click OK, and then you select the data, and then you click Next, and that brings up the heat map dialog. Now, this heat map dialog could have also been accessed under graphical tools heat map. So you always have, you can either use the wizard or you can use the direct menu selection. So for the heat map, I'm going to pick my row categories, major complaint, and then for my column categories, customer type. So this is customer data, which is a data set that is used in our workbook. I have major complaint by customer type, and this creates a heat map. This is essentially a pivot chart, a pivot table that's color coded with dark blue showing the minimum and dark red showing the maximum. All right, so it's just a nice summary table of counts. And this is for the heat map. If we could also look at other things. So for example, maybe I want to look at major complaint customer type, and I'd like to look at overall satisfaction. Now, I can specify mean, or I can specify various statistics and click OK. And it's going to give me a heat map showing me, in this case, the maximum overall satisfaction and the minimum overall satisfaction. All right, so that's just, again, that's an alternative to the pivot table. And we also have an easy pivot utility, but the heat map is something we just added in version 10, so I wanted to show that to you. I want to show you another example that highlights the power of the heat map. And for that, I have data that was extracted from the World Bank. And what it is mobile cellular subscriptions per 100 people from 1990 to 2021, and broken out by region, so East Asia and Pacific, Europe and Central Asia, Latin America and Caribbean, Middle East and North Africa, North America, and South Asia. So I'm going to create a heat map. I'm going to go Graphical Tools, Heat Map, and I'm going to use region as my row category, year as my column category, and mobile cellular subscriptions as my optional numeric response, and I will use the average for that. So this creates a heat map that I can now look at year by year. So remember, dark blue is minimum and dark red is maximum. So as we can see in 1990, very low mobile subscriptions. And then as you go through your years, you can see, and then again by region, the increase in the usage of cellular phones. In fact, in 2021, you have people that have 2 subscriptions, so one for work and one for private. So in East Asia and Pacific, in Europe, Latin America, Middle East and North Africa, you actually have, on average, more than 1 subscription per person. So very high usage in that regard. So it's a very nice way of being able to visually see the transition, increased usage on a year-to-year basis, and then by region. Okay, so that's the heat map. The next graphical tool we'll look at are histograms. So I'm going to go back to my customer data. Customer data, I should mention, the primary metric of interest is overall satisfaction on a 1 to 5 scale, where 1 is very dissatisfied and 5 is very satisfied. And we have customer types 1, 2, and 3. And so we're interested in what are the factors that influence overall satisfaction. We also track responsive to calls, ease of communication, staff knowledge, things like that. So this is the primary data set that we'll be using and the primary data set that is used in our workbook. So now I'll do graphical tools, histograms, and descriptive statistics. So I'll do overall satisfaction by customer type, and this will create a stacked histogram for customer type 1, customer type 2, and customer type 3. So we can see here, customer type 2 has a skewed left distribution, but that's a good thing. Even though customer types 1 and 3 have normal data, you can see that by the Anderson-Darling p-value. The fact that customer type 2 has non-normal data is actually a good thing, because you have more 4s and 5s and fewer 3, 2s, and 1s. So you can see that by looking at the histograms and quickly comparing, and then you can compare the means, and you can see the mean here of 3.4 versus 4.2 versus 3.6. So these are your descriptive statistics. So nice, quick and easy way of comparing continuous data. Then to complement this, we have Boxplots. So then that's what we'll look at next. We'll go under graphical tools, Boxplots, and we'll look at overall satisfaction versus customer type, and we'll show the mean and show the legend. So the Boxplot is more concise presentation of the data. The bottom bar is the 25th percentile, the top bar is the 75th percentile, the solid bar is the median, the dashed line is the mean, and this corresponds to a potential outlier. The light circle is a potential outlier, a solid circle is an extreme outlier. So again, nice, quick and easy way of comparing using Boxplots. And next, we're going to look at the Scatterplot Matrix. So graphical tools, Scatterplot Matrix, and I will look at overall satisfaction. We'll look at responsive to calls, ease of communications, and staff knowledge. These need to be continuous variables, all right? You don't want to be putting discrete variables into your Scatterplot Matrix. So strictly comparing the relationships between continuous variables. This creates Scatterplot Matrix. Here we can look at overall SAT versus responsive to calls. So we see an R-square of 68%. So that's a good moderate strength relationship. Usually over 80 is considered strong, and 50 to 80 is in the moderate. And so here we have overall SAT versus ease of communication. And here we have overall SAT versus staff knowledge. So it's interesting that ease of communication and responsive to calls were the primary drivers for overall satisfaction, that actual staff knowledge was not considered as important. Again, this is a specific set of data. I'm not saying that that isn't important, but it's just to point out that whenever you're doing a study like this, you want to identify which variables are drivers, but also which variables are not drivers. And useful information in both, where you do have relationships and where you do not have relationships. So that's the Scatterplot Matrix. Another graphical tool that we've just added in version 10 is the XYZ contour surface plot. And this is a very powerful tool. Overall SAT is the Z, and we have ease responsive to calls as the Y, and ease of communications as the X. The math behind this is rather detailed, advanced. It includes inverse distance weighting, Acuminus polynomial, and biharmonic spline as methods of interpolation and extrapolation. The way this contour is going to work is it doesn't require a model. It's not like a contour based on a linear regression, which, by the way, of course, we can do, and I'll be demonstrating that shortly. But this is strictly based on the data. It's just interpolation methods. So the thing is, there are lots of different methods. And so what we have, and this is something unique to SigmaXL, is that we use a leave one out cross-validation method to determine which of the methods is the best. So if you have smooth data, then you're going to get something like an Acuminus polynomial or a biharmonic spline. If you have less smooth data, then you're probably going to get something with inverse distance weighting. So if I run this, I'm using the automatic method. You can see here, you get your overall satisfaction. You can see that with high ease of communication and high responsive to calls, we get maximum overall satisfaction. You can do cool things with this. You can right click and you can go 3D rotation, and you can change the rotation to get a different camera angle on the graph. And that's pure Excel in terms of what we're doing here. But SigmaXL used the methods of interpolation to take the raw data and produce this surface plot. The contour plot, I think, is not quite as useful in this particular tool, but we give you both. So just depending on what it is that you want to do. You are also given the method that was used by cross-validation with an R-square, the leave one out cross-validation. And if you go back and try different methods, then you will get reports on the root mean square error for the cross-validation. So you can kind of get an idea of which, if you want to play with it, try different things out, you can do that as well. But the easiest way to do it is just go automatic. So that's the XYZ contour. And the last graphical tool that we're going to look at is the analysis of means. And that's really a bridge to hypothesis testing. The analysis of means is a graphical tool, but it's kind of like a graphical one-way ANOVA, but it's not exactly the same, or like a hybrid between an ANOVA and a control chart. And you'll see in a minute. Actually, it is a very useful complement to the ANOVA. So if I do ANOM normal one-way analysis of means one way, then I can say I'm going to do overall SAT as the Y, and I'm going to do customer type as the X. And this gives me my analysis of means. So in analysis of variance, the null hypothesis is that the pairwise means are the same. So mean 1 equals mean 2, and then mean 1 equals mean 3, and then mean 2 equals mean 3. But in the analysis of means, the null hypothesis is that the observed mean is equal to the grand mean. All right, so it's a slightly different null hypothesis than the ANOVA, but it is a very useful tool to, it's actually much easier to use than a whole bunch of pairwise combinations. All right, so that's the problem when, with 3, it's not a problem, but when you have multiple levels and you're trying to interpret an ANOVA, that gets a lot trickier because you have lots of pairwise combinations possible. Whereas with the analysis of means, it's just each group mean compared to the grand mean. And so we see here that customer type 1 has a significantly lower mean than the grand mean. Customer type 2 has a significantly higher mean than the grand mean. So that's good. Remember, bigger is better because it's a satisfaction score. So we would say, well, okay, so what is it that customer type 2 is doing that's different from customer type 1? And we could start looking at best practices. And we already know from the previous graphical analysis that things like overall satisfaction and ease of communications are drivers. So we could look at what are they doing in those areas that would help us to improve our customer satisfaction. All right, so that's the ANOM. And now we're going to switch gears and we're going to look at descriptive statistics. We'll start with descriptive statistics and then we'll move to hypothesis testing. Let's see, so we go statistical tools. Yeah, I'll show you hypothesis test selection guide in a moment, but I want to start with descriptive stats. And here I'm going to do overall by customer type. I can select options and I can do additional descriptive, additional normality, outlier and randomness tests, percentile report, but I'm not going to do that. I'm just going to go with the defaults. And so again, I can compare overall satisfaction for customer type 1 versus 2 versus 3. So each of the descriptive statistics, the mean, the standard dev, notice the standard dev is lower for customer type 2. So not only do they have a higher mean sat score, they have a lower standard deviation. So they're consistently happier. And then you can compare the percentiles. We have the confidence intervals for the mean, confidence intervals for the standard deviation. We have the normality test. So as we saw earlier, customer type 2 has non-normal data, it's skewed left. But keep in mind, in this particular case, that's not a bad thing because it means you have happier customers. More 4s and 5s and fewer 3s, 2s, and 1s. All right, so that's descriptive statistics. Now, what I want to do is I want to show you the hypothesis test selection guide. So again, much like the graphical tool selection guide, you start with what kind of data do you have, continuous or attribute discrete? How many samples do you have? 1 sample or 2 sample? Is it a one-way or a two-way? And then what are you interested in comparing? Mean, standard deviation, median? So depending on what you pick, the options that are available to you are given here. And then when you click OK, it will take you straight into that particular menu choice. So let's go to attribute. If I go to attribute, let's say I have 2 samples. So if I want to compare, perhaps I have vendor A, vendor B, and I'd like to compare their failure rates. So I can do a 2-sample comparison of proportions. And I can do either a 2 proportions test and confidence interval, or I can do a 2 proportions equivalence test. I'm not going to get into equivalence tests here. It is 2 one-sided t-tests, but what we will do is we will look at the 2 proportions test and confidence interval. That brings up a template. So in the 2 proportions test, you have a template and you simply populate the number of events and the sample size. So if I look here and I have, for sample 1, 1 defect out of 10, and sample 2, I have 2 defects out of 10, that's a fail to reject. The probability value, actually I'm using Fisher's exact right here. I can actually change that. I can go to normal approximation, but we'll stay with Fisher's exact, which is what you want for small samples anyways. So this is a fail to reject. Now, if I, let me use the same percentages, but increase the sample size. So what if I go 10 out of 100, and I go 20 out of 100? Okay, let's try, let me try increasing the, let me go 10, let me go 100 out of 1,000, and then go 200 out of 1,000. All right, so that is a reject, that the p-value is less than 0.05. We reject the null hypothesis that the proportions are the same, and yet the actual numbers, the 10% and the 20%, are the same. So it just shows you, as your sample size increases, the ability to detect a statistically significant difference increases. This relates to the power of the test. I like to just illustrate this with a small sample size versus a large sample size, maintaining the same difference in proportions. All right, so that gives you your two proportion test. Now, let's switch over to continuous data and go back to the menu, and we'll look at the two sample t-test. So the two sample t-test, the null hypothesis is that the means are equal. So I'm going to compare, I'm going to do overall satisfaction by customer type. The null hypothesis is that the mean difference is 0. I'll assume equal variances, and I'm going to display test assumptions report. Now, because we have customer types 1, 2, and 3, you are prompted to select 2 from the list. So we'll do comparison of 2 versus 3. And this tells us that we reject the null hypothesis that the means are equal. So customer type 2 has a higher mean satisfaction score. And you are also given various assumptions that are being tested here. Normality. So it turns out that, as we've seen before, customer type 2 has non-normal data. That doesn't mean it's a problem. It's just an alert. And yellow is caution, green is good to go. Red is a problem that needs to be investigated further. Now, what happens is that even though you have non-normal data for customer type 2, the two sample t-test is still quite robust to the assumption of normality. So what we do here is SigmaXL has a set of formulas that are used that test for minimum sample size required to maintain robustness. And there's actually a standalone calculator that does that under statistical tools, basic templates, minimum sample size for robust t-tests in ANOVA. For time, I'm not going to get into that, but I'm just mentioning that we did that using extensive Monte Carlo simulations. So after testing normality, we also say whether or not the normality is a problem for the particular test. So if this is yellow, then you need to consider using non-parametric tests like the Mann-Whitney, whereas here we're good with our minimum sample size requirement. Also, the outlier, we saw that in the box plot. You have a potential outlier, so that's just an alert. You also have a test for randomness, and we're good here. The data are random, and we also test for equal variance. So because there's non-normality, it automatically used the Levine's test. If the data were both normal, it would have used the F test for equal variances. So that's the two sample t-test. And now I want to show you the two sample comparison tests. So if we go statistical tools, two sample comparison tests, and this is actually very similar, but is going to give you more information. And again, we'll pick customer types 2 and 3. So now, similar to the two sample t-test, we have the normality test. And because one of the groups has non-normal data, it uses the Levine test rather than the F test. In here, the p-value is greater than 0.05. That's a fail to reject, so we can assume that the variances are equal. So again, had the data been normal, then the F test would have been highlighted. Because there is non-normality, the Levine's test is highlighted. Then, depending on the state of test for equal variances, the two-sample t-test for assume equal variance is given, and the two-sample t-test for assume unequal variance is given. And the one that is highlighted is the one that's appropriate based on the fact that we used Levine's test and it was a fail to reject. Finally, you have the Mann-Whitney test, so you can compare that. So that's the robust test for medians. Okay, so that's a nice, succinct, all-in-one two-sample comparison test. Now let's switch over and we'll look at one-way ANOVA. So analysis of variance, we saw the analysis of means. Graphical, now we're going to look at the one-way ANOVA. And the null hypothesis is that the means are equal. And then we'll look at the pairwise comparisons as well. So overall satisfaction by customer type. Under options, I can specify if I want Fisher, Tukey, Dunnett. Again, we don't have time to get into all this, but Tukey is a good method for multiple comparison of means. We'll also display the analysis of means normal one-way chart as a complement to the analysis of variance. So I'll run that. And based on the p-value, we can conclude that the means are not equal. And again, the alternative is that at least one pair of means are different. Then you go down to your pairwise mean difference chart, and the ones that are in red are statistically significant based on the Tukey probabilities. So you can say 2 versus 1 is different, 3 versus 2 is different, but 3 versus 1 is not different. Again, like we saw earlier, all of your assumptions are tested here. So this kind of is an extension of the two-sample t-test, but now allows for multiple comparisons. So that's the one-way ANOVA, and as well, we have the residuals analysis. So you have your residuals and you have your analysis of means chart that we saw earlier. You can get that directly by using the ANOM, or you include that as part of your one-way ANOVA. Under the one-way ANOVA, we have the interval plot. So you have a nice visual to compare. So these are the means and the 95% confidence interval. And you can see that there is no overlap between customer type 2 and 3, and no overlap between customer type 2 and 1, but lots of overlap between 1 and 3. This is under the assume equal variances option. So it's pooled using the pooled variance to compute the confidence intervals. All right, so that's the one-way ANOVA. And now we'll look at correlation matrix. So we'll go to statistical tools, correlation matrix, and we'll do overall satisfaction, responsive, ease, staff knowledge. That's fine, we'll keep it just with these, and then we'll click OK. And this is now, so we saw the correlation, sorry, the Scatterplot matrix. This is the correlation matrix. And what we have here is what we do is we do both the Pearson and the Spearman rank. So the Pearson assumes bivariate normality, and the Spearman is robust. It's basically correlation of ranks. So if you do not have bivariate normality, you should use the Spearman rank. But the Pearson correlation is more powerful if you do have the bivariate normal. So which one do you pick? Well, whichever one is highlighted, because in the background, SigmaXL does a hypothesis test on bivariate normality, and then just kind of tells you, all right, so in this particular case, we recommend using the Spearman rank correlation. Both are given. You have your correlation and you have your p-values, and if it's red, it means it's significant. And again, as we saw, the staff knowledge, we're not seeing anything significant under staff knowledge. Now, we're ready to kind of tie it all together with advanced multiple regression. So what we'll do now is we'll go to advanced multiple regression. You have regular regression, but advanced multiple regression includes lots of features that are very useful. So we're going to do overall satisfaction responsive to call, ease of communications. We'll put in customer type as our categorical predictor. I want to standardize my continuous predictors. So I'm going to subtract the mean, divide by the standard deviation, so that each of the continuous predictors is of equal units. That makes it easier to interpret. In terms of the prediction formula, that's all taken care of automatically. So you can use, even though we're standardizing, you can easily still make predictions. Coding, we'll use the default dummy coding, 1-0. And we'll include residual plots. We're not going to do Box-Cox transformation. So let's just go ahead and run that. So the first thing that happens is we're prompted to specify the model. So if you're only interested in main effects, you would just hit select all. But I'm interested in interactions as well. So what this will do, that's why I standardized. So I can now include, not only will I look at responsive to calls, ease of communications, customer type, I'm going to look at responsive by ease, responsive by customer type, and ease by customer type. So if you're familiar with designed experiments, this is essentially what we do in DOE when we have linear terms and two-way interactions. But we can do this with historical data as well. And so I'm going to go ahead and run that. And now I have my R-square, which is 92.88. That's very good. More importantly is the fact that R-square predicted is very good, which is the 89.9. R-square predicted is leave one out cross-validation method to compute the R-square. So that actually is more useful than a regular R-square and even R-square adjusted. So there's a lot of information here. I don't have time to cover everything, but again, we'll look at the p-values. The VIFs are below 5, so we're okay. We could do model refinement. We have automatic stepwise regression, but because of time constraints, we won't show that. But we can go through and we can refit the model. And there's various other tests that are in here. I just want to focus on the basics. So I have my Pareto chart. So here I can see that responsive to calls, ease of communications, and the responsive to calls by ease of communication interaction are the important significant predictors. It turns out when you include responsive to calls and ease of communications, customer type kind of drops out in terms of significance. So that's an interesting point here. Now, what I want to do is I want to show you, let's say we'd like to, this of course is a pretty straightforward thing, and this is the equation that's used. Notice that these are if statements to handle the categorical customer type. So if I just change this to customer type 2, then that changes my predicted response, and I have my confidence interval and my prediction interval. But I can specify, I'd like to say what settings will maximize my satisfaction. I run optimize, and I click yes, and no surprise, maximum responsive to calls, maximum ease of communications is what gives me my maximum satisfaction score. Now, customer type 1 was not expected because earlier we saw customer type 2 had the higher SAT scores, but once in your model, the model is being driven by responsive to calls and ease of communications, and customer type is actually less important here. Really, if I change it to 2, oh, and the interaction term is also at play here. So what's useful when you're looking at this is also looking at the contour plot. So now, similar to the XYZ contour plot, this is now based on the regression model, and the curvature is that interaction term. So we can see that maximum responsive to calls, maximum ease of communications gives us our maximum overall satisfaction. All right, let me do process capability for normal data. And for that, I have some interesting data called delivery times, which was hotel breakfast delivery times showing the deviation. And we have a spec limit of plus or minus 10 minutes. And so if we want to do basic process capability. We can do histograms and process capability, and I'll do delivery time deviation. And then the upper spec limit is 10, the target is 0, and the lower spec limit is -10. And then I'll run that, and that gives me my histogram, shows you the spec limits and your various capability indices. So this is not a capable process. Not only do you have to shift the mean, you have to reduce the variability. We also have what is also known as the 6-pack. We call it the capability combination report. So if I do delivery time deviation and I do upper spec limit, target, and lower spec limit -10, now you have your histogram, your normal probability plot, your process capability, and your control charts. So you have your individuals and moving range. So it's all in one report. That's your combination report. Now for non-normal, we not only have Boxplots, we have various families of distributions. So let me switch over to non-normal cycle time, and I'll go to process capability, non-normal, capability combination report, non-normal, and then cycle time. And the cycle time spec limit, upper spec limit is 1000. I'm going to use the Boxplots transformation. You can use Johnson. You can go automatic best fit. You can specify a distribution. You have a variety of log normal with threshold, exponential, Weibull, beta, gamma, logistic. We'll keep it simple. We'll go with Boxplots. We'll use rounded lambda and run OK. And this gives us our capability combination report. It's used a logarithmic transformation, which is typical for cycle time. Looking at the data with the Boxplots curve fit, this is the Boxplots transform data. So a straight line means the Boxplots is doing a good job of transforming. You also have the Anderson-Darling normality test before and after. So before, significantly not normal. After, the distribution, it's a good fit. It's a fail to reject. So before was not normal, after is normal. And the PPKs and the CPKs are all now based on the transform data and the transform spec limit. All right, so that's your Boxplots. Then you have your control chart. The first chart is the percentile-based control chart. So the reason for that is so that you can actually see the raw data. Then you have the Z-score transformed control chart. And the nice thing about that is that you can actually use your test for special causes. And that includes both the individuals and the moving range. Okay, so that's the process capability for normal and process capability for non-normal. Let me go to the control chart selection tool. So if I go to control charts, I have a control chart selection guide. So again, continuous data, discrete data, depending on the data type, whether you have individuals or subgroups, that will then present to you the options that are available for continuous charts that include Shewhart, rare events, time-weighted like EWMA, trend charts. And if I want rare events, I can go to T or G. If I have time-weighted, I can do EWMA or QSUM, or I can do a trend chart. All right, so let's say I want to create a Shewhart individuals chart. I'll just do a Shewhart chart of overall satisfaction. And that's my control chart for overall satisfaction. And actually, I'm going to use a different data set. I want to show you split limits. I have a before and after improvement. So I have 20 data points before and 20 data points after. So I can go to SigmaXL, control charts, individuals, and then I'll do distance is the Y. We'll put operator as the optional x-axis label, and then we'll go to advanced options, and we'll go historical groups before after. Then what that does is that gives me a split control chart showing me my process before improvement and my process after improvement.
This concludes the product demo for SigmaXL version 10. For more videos, visit www.sigmaxl.com or join us on YouTube. Thank you for watching.